Tonight, we're diving into something that genuinely keeps astronomers awake at night. And no, it's not because they're scared. It's because they're confused. Actually, deeply, genuinely confused. Because out there in the vast expanse of space, we've discovered things that simply don't make sense. Things that shouldn't exist according to everything we understand about the universe. Things that break the rules we thought were unbreakable. And here's what makes this so fascinating. I'm not talking about science fiction. I'm not discussing theories or wild speculation. I'm talking about real observations. Things we've actually seen with our own instruments. Things we've measured with precision equipment. Things that are out there right now, at this very moment, doing whatever strange thing they do. And we have absolutely no idea why. Over the past few decades, as our telescopes have become increasingly sophisticated and our ability to observe the universe has improved dramatically, we've stumbled across discoveries that have left the brightest scientific minds scratching their heads in bewilderment. Some of these discoveries fundamentally challenge our understanding of physics. Some of them suggest there might be processes occurring in the universe that we haven't even begun to comprehend yet. And some of them, well, some of them are just plain weird, strange in ways that make you question whether we really understand anything at all. Before we dive deep into these mysteries, if you enjoy these explorations into the unknown corners of space, a quick like or subscribe would really help this channel grow and bring you more content like this. It's a small thing on your end, but it makes a massive difference in our ability to keep producing these deep dives. Now, let's get into it. Let me start with something that happened on August 15th, 1977. A day that would become one of the most intriguing dates in the history of the search for extraterrestrial intelligence. A man named Jerry Amon was reviewing data from the Big Ear Radio Telescope at Ohio State University. This telescope was part of SETI, the Search for Extraterrestrial Intelligence program. Every single day, it scanned the sky, listening carefully for radio signals that might indicate intelligent life somewhere out there in the cosmos. Most days, the data was exactly what you'd expect. Background noise from space, nothing unusual, nothing exciting, just the cosmic static that fills the universe. But on this particular day, Eman saw something that made him grab a red pen and write a single word in the margin of the printout. That word was wow. That's why we call it the wow signal. And that simple expression of amazement has become one of the most famous annotations in the history of astronomy. The signal lasted exactly 72 seconds. During that time, it was 30 times stronger than the background noise. It came from a very specific direction in the constellation Sagittarius. And here's what makes it so genuinely interesting, so compelling that we're still talking about it almost 50 years later. The signal's frequency was around 1,420 megahertz. That's right near what we call the hydrogen line, a natural frequency that's intimately associated with hydrogen atoms in space. Now, why does that matter? Why is this frequency significant? Because hydrogen is the most common element in the entire universe. It's everywhere. If you were an alien civilization trying to send a signal that other civilizations might recognize, that other intelligent beings might understand as artificial, you might choose a frequency related to hydrogen. It's like choosing a universal language based on something everyone would know. It's a frequency that any civilization capable of radio astronomy would immediately recognize as significant. The Big Ear telescope had two receivers that scanned the same patch of sky 3 minutes apart. The signal showed up on the first receiver, clear as day, but it didn't show up on the second. That means it lasted less than 3 minutes, probably closer to those 72 seconds based on the data we have. It was a brief flash of something extraordinary. Since 1977, astronomers have gone back to that same spot in the sky dozens and dozens of times. They've used more powerful telescopes. They've listened at the same frequency and at nearby frequencies. They've searched meticulously for any sign of the signal returning. They've spent countless hours hoping to catch it again. Nothing. Absolutely nothing. The wow signal was a one-time event. It appeared once and vanished forever. Now, let me be absolutely clear about the uncertainty here. We need to be honest about what we don't know. The signal could have been artificial, created by some intelligence. Or it could have been natural, produced by some cosmic phenomenon we don't understand. The Big Ear telescope couldn't pinpoint locations with extreme precision. So we know the general direction, the rough area of sky, but not the specific source. We can't point to a particular star or galaxy and say, it came from there. Some scientists have proposed natural explanations. Maybe it was a signal from a passing comet. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds, creating a brief burst of radiation. In 2016, a researcher named Antonio Paris suggested that two comets, known as 266 P/Christensen and P/208Y2, were in that region of space at the time. It was an interesting hypothesis. But there's a significant problem with the comet theory. The signal was incredibly narrow band. It occupied a very specific, very precise frequency. Natural sources usually produce signals across a broader range of frequencies. They're messy. They spread out. The narrowness of the WOW signal is more consistent with an artificial source, something deliberately transmitting on a carefully chosen frequency. It's the kind of signal an intelligent civilization might send. Other scientists have suggested it might have been interference from Earth, a satellite passing overhead, an aircraft flying by. Some ground-based transmitter that happened to send a signal at just the right time, bouncing off something in just the right way to appear to come from space. But the Big Ear telescope was specifically designed to filter out terrestrial interference. And the signal came from a direction that was not consistent with any known satellite or aircraft position at the time. So what was it? Honestly, it remains completely unexplained, and that's precisely what makes it so fascinating. Nearly 50 years later, the WOW signal remains one of the most intriguing unexplained observations in the entire history of SETI. The fact that it never repeated is both incredibly frustrating and deeply significant. If it was an alien civilization, why would they only transmit once? Why haven't we heard from them again? Maybe they were using what we call a lighthouse strategy, sweeping a beam of radio waves across the galaxy, and we just happened to catch it for that brief 72-second moment when it passed across Earth. Maybe it was a one-time broadcast, an announcement, a greeting sent out into the void. Maybe it wasn't meant for us at all. Just an accidental spillover from some other communication between two distant points in space. Or maybe, just maybe, it wasn't aliens at all. Maybe it was some natural phenomenon we simply don't understand yet. The universe is absolutely full of processes that emit radio waves. Pulsars spinning rapidly, sending out beams of radiation. Quasars powered by supermassive black holes. Magnetars with magnetic fields so strong they defy imagination. Supernova remnants expanding through space. We're constantly discovering new types of radio sources. Maybe the WOW signal was something natural that we've just never seen before or since. The truth is, the answer may never come. The signal lasted 72 seconds in 1977 and never came back. It's a mystery frozen in time, preserved in that single printout with Jerry Emmons' red pen marking. But it's also a powerful reminder of how much remains unexplained about the universe we inhabit. Somewhere out there, in the direction of Sagittarius, something sent out a powerful narrow-band radio signal, and we happened to catch it. That's either the most incredible coincidence in the entire history of astronomy, or it's evidence of something truly extraordinary. Either way, it's strange. And it's why, almost 5 decades later, people are still talking about, still studying, still wondering about the WOW signal, Tabby's star and odd radio circles. Now, let's talk about something that's happening right now. Not in the distant past, but ongoing. A star that's been driving astronomers absolutely crazy since 2011. Its official designation is KIC 8462852, but most people call it Tabby's star, named after astronomer Tabetha Boyajian, who led the research team studying it. and first brought its bizarre behavior to widespread attention. Tabby's star sits about 1,460 light-years away from Earth, in the constellation Cygnus. From a distance, it looks like an ordinary star. It's slightly larger than our Sun and slightly hotter. Nothing about it should make it special or noteworthy. But in 2011, the Kepler Space Telescope noticed something genuinely weird. Something that didn't fit any pattern we'd ever seen before. Stars dim sometimes. That's completely normal. If a planet passes in front of a star from our perspective here on Earth, the star's light drops slightly. That's actually how we detect most exoplanets. When Earth passes in front of the Sun from another star's perspective, the Sun's light would dim by about 0.01%. Tiny, but measurable with sensitive equipment. Jupiter, being much, much larger, would cause the Sun to dim by about 1% if it passed directly in front. That's the kind of dimming we expect from planets. Regular, predictable, small. Tabby's star doesn't do that. Not even close. In 2011, its light dropped by 15%. Then it came back up. In 2013, it dropped by an astounding 22%. Then it came back again. The dimmings were completely irregular. They didn't repeat at predictable intervals like planets orbiting on regular paths. They lasted different amounts of time. Sometimes the star would dim a little, sometimes dramatically. 22% is absolutely enormous. That's not a planet. A planet the size of Jupiter would only block 1% of the star's light. To block 22%, you'd need something absolutely massive, something roughly as large as the star itself. The initial discovery set off an absolute frenzy of theories in the astronomical community. What could possibly be blocking that much light? Here's where things got really interesting, where this story took a turn that captured public imagination worldwide. Someone suggested it might be an alien megastructure. The idea comes from a hypothetical concept called a Dyson sphere, proposed by physicist Freeman Dyson back in 1960. Dyson wondered what an extremely advanced civilization would do if it needed enormous amounts of energy, far more than a planet's worth of solar panels could provide. Eventually, he reasoned, they might build structures around their star to capture a significant portion of its energy output. Not a solid shell, which would be structurally impossible, but a swarm of energy-collecting satellites orbiting the star at various distances and angles. If you were building something like that, if you were constructing this massive array of solar collectors, it would block varying amounts of the star's light as the structure orbited. It would be irregular, depending on the configuration. It would dim the star by large, unpredictable amounts. It would look exactly, precisely, like what we were seeing with Tabby's star. Now, before you get too excited, let me be absolutely clear about something. Most astronomers don't think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation from a scientific standpoint. But here's the thing that made this so remarkable. We had to seriously consider it because we couldn't explain the observations any other way. That's how weird this star is. When scientists can't think of natural explanations that fit the data, they have to consider unlikely possibilities. So, if it's not aliens, what is it? Scientists propose several natural explanations, each attempting to account for this bizarre behavior. Maybe there's a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, they would block light irregularly. Their dust tails would create uneven dimming patterns. This was a leading theory for quite a while, and had some compelling aspects to it. But there are significant problems with the comet theory. Where did all these comets come from? You'd need an absolutely enormous number of them to block 22% of the star's light. We're talking about a truly massive collection of comets. And comets produce dust, which would absorb and re-emit the star's light. This would make the star appear redder when it's dimmed. But Tabby's star doesn't do that. The color stays essentially the same, even when it's dimmed significantly. Another theory suggested maybe there was a recent catastrophic collision. If two large objects, perhaps planets or large asteroids, smashed together near the star. The resulting debris cloud could block light irregularly as it spreads out through space. But again, we'd expect to see excess infrared radiation from warm dust heated by the star. We don't see that signature. Some scientists suggested the dimming might be caused by the star itself. Maybe it's what we call a variable star, one that dims naturally due to internal processes. But Tabby's star doesn't show the characteristic patterns of known variable stars. The dimming pattern is too irregular, too unpredictable. Then, in 2017, astronomers made another crucial observation. They caught Tabby's star dimming again, and this time observed it simultaneously across multiple wavelengths of light. What they found was genuinely interesting and provided a major clue. The dimming was more pronounced in blue light than in red light. That's consistent with dust blocking the starlight. Small dust particles scatter blue light more effectively than red light. It's the same physical principle that makes Earth's sky appear blue during the day. So maybe it is dust after all. But if it's dust, where is it coming from in such quantities? Why is there so much of it? Why is the pattern so completely irregular and unpredictable? The latest observations suggest that Tabby's star might have a large, complex debris field around it, perhaps from a destroyed planet or a massive collision or some other catastrophic event we can only guess at. The debris blocks light irregularly as it orbits at different distances and angles. This is the current leading explanation, but it's not fully satisfying. The complete picture remains frustratingly unclear. And here's what makes this even stranger, even more compelling. Tabby's star is still doing it. We've now watched this star for more than a decade. It keeps dimming in weird, unpredictable ways. We have multiple data sets from different telescopes using different instruments. The phenomenon is absolutely real. It's not a measurement error. It's not an instrumental glitch. Something is actually blocking the light from this star in ways that remain genuinely puzzling to this day. As of 2025, Tabby's star remains one of the strangest, most perplexing objects in the night sky. Out of hundreds of billions of stars in our galaxy alone, this is the only one that behaves like this. We've never seen anything else quite like it. Maybe one day we'll figure it out completely. Maybe we'll discover it's a natural process we just haven't encountered before. Or maybe, just maybe, it's something else entirely, something we haven't even thought of yet. Now, let me tell you about something that scientists discovered in 2019 that absolutely shouldn't exist according to our understanding of the universe. They're called odd radio circles, or ORCs for short. The name is absolutely perfect because they are odd. They're circles. And we only see them when we observe in radio wavelengths. Here's what they look like. If you point a sensitive radio telescope at certain specific parts of the sky, you see a nearly perfect circle. The circle is enormous, hundreds of thousands of light years across. And here's the genuinely weird part that has scientists baffled. There's usually a galaxy at the center of the circle, but we can't figure out what's causing the circle itself. Astronomer Anna Kapinska and her team first spotted these mysterious structures while using the Australian Square Kilometre Array Pathfinder, a cutting-edge radio telescope array in Western Australia. They were conducting a survey called the Evolutionary Map of the Universe, scanning massive portions of the sky to map radio sources. And that's when they saw them. Perfect circles. Massive circles. Circles that weren't supposed to be there. At first, they thought it might be an error with the telescope. Maybe a glitch in the data processing. Maybe some kind of artifact created by the imaging software. So they checked everything meticulously. They reviewed the calibration. They examined the instruments. They looked for any possible source of error. But no, the circles were real. They were actually out there in space, emitting radio waves that had traveled across vast cosmic distances to reach us. Since that initial discovery, astronomers have found several more of these odd radio circles. Each one is slightly different, but they all share common characteristics. They're circular or nearly circular. They're absolutely enormous in scale. They're only visible in radio wavelengths, meaning if you looked at the same spot with an optical telescope, you'd see nothing unusual at all. And they all seem to have a galaxy at or near the center of the circle. So what are they? What could possibly create such a massive, perfectly circular radio structure? Scientists have proposed several theories, each trying to explain this bizarre phenomenon. One idea is that they might be spherical shock waves. Imagine a massive explosion happening in or near the central galaxy. Maybe two supermassive black holes collided. Maybe there was an enormous burst of star formation followed by countless supernovae going off in rapid succession. Such an explosion would send a shock wave expanding outward in all directions, creating a sphere. From our perspective on Earth, we'd see that expanding sphere as a circle, the same way you see a soap bubble as a circle when you look at it from any angle. But here's the problem with the explosion theory. These circles are enormous, truly enormous. To create a radio circle hundreds of thousands of light years across, you'd need an explosion so powerful, so incredibly energetic, that it would dwarf anything we've ever observed. We're talking about energy levels that make supernovae look like firecrackers by comparison. Could galaxies produce explosions that powerful? Maybe, but we've never seen anything quite like it before. Another theory suggests these might be related to what we call radio galaxies. Some galaxies have supermassive black holes at their centers that shoot out massive jets of particles and radiation. These jets can extend for millions of light years. When these jets interact with the surrounding intergalactic medium, they can create structures visible in radio wavelengths. Maybe odd radio circles are some kind of unusual configuration of these jets, seen from a particular angle or at a particular stage of evolution. Some scientists think they might be related to fast radio bursts. These are brief, incredibly powerful pulses of radio waves that come from distant galaxies. We don't fully understand what causes fast radio bursts either, so this theory essentially explains one mystery with another mystery. But maybe a fast radio burst or something similar could create these expanding circles under certain specific conditions we haven't figured out yet. Here's what makes odd radio circles especially frustrating for astronomers. They're so faint and so large that they're incredibly difficult to study in detail. You need extremely sensitive radio telescopes covering large areas of sky. You need lots of observation time. You need sophisticated data processing. And even when you have all that, the circles remain stubbornly mysterious. The galaxies at the centers of these circles are typically quite distant, often billions of light years away. That means we're seeing them as they were billions of years ago, when the universe was significantly younger than it is today. That temporal distance makes everything harder to understand. We're trying to figure out what happened in these galaxies billions of years in the past, based on faint radio signals that have been traveling through space for eons. As of right now, as of 2025, odd radio circles remain completely unexplained. We have theories, certainly. We have ideas and hypotheses, but we don't have a definitive answer. We don't know what causes them. We don't know why they form. We don't know if they're common or rare. We've only found a handful of them so far, but that might be because they're incredibly hard to detect rather than because they're genuinely rare. What we do know is that they're real. They exist. They're out there right now, enormous circular structures of radio emission surrounding distant galaxies. They're doing whatever it is they do, and we're only just beginning to notice them. As our radio telescopes become more sensitive, and as we survey more of the sky in radio wavelengths, we'll likely find more odd radio circles. And hopefully, with more examples to study, we'll start to understand what they actually are. Giant cosmic structures and the Botez void. Now let's discuss something that challenges one of the fundamental principles of modern cosmology. In 2021 and 2022, astronomers discovered two massive structures in the universe that, according to our understanding of how the universe formed and evolved, simply shouldn't exist. They're called the Giant Arc and the Big Ring, and they're so large, so impossibly enormous, that they call into question some of our most basic assumptions about the cosmos. The Giant Arc was discovered by doctoral student Alexia Lopez at the University of Central Lancashire. She was analyzing the distribution of galaxies in deep space, mapping where galaxies are located relative to each other, looking for patterns in the large-scale structure of the universe. And that's when she saw it. A giant curved structure of galaxies stretching across an absolutely mind-boggling expanse of space. How big? The giant arc is 3.3 billion light-years long. Let me repeat that to make sure you grasp the scale. 3.3 billion light-years. To put that in perspective, light from one end of this structure takes 3.3 billion years to reach the other end, even traveling at the speed of light, the fastest speed possible in the universe. This structure is so large that it spans roughly 1/15 of the entire observable universe. Then, in 2022, Lopez discovered another massive structure in roughly the same region of space, the Big Ring. This one is 1.3 billion light-years in diameter. Not as large as the giant arc, but still absolutely enormous. Still almost incomprehensibly vast. And here's what's particularly interesting. The Big Ring and the giant arc appear to be in the same cosmological neighborhood. They might even be related somehow, perhaps part of an even larger structure or pattern we're only beginning to glimpse. Now, why is this a problem? Why does the existence of these structures challenge our understanding of cosmology? It all comes down to something called the cosmological principle. This is one of the foundational assumptions of modern cosmology. It states that on very large scales, the universe should be homogeneous and isotropic. That's scientific jargon that means the universe should look pretty much the same in all directions, and matter should be distributed fairly evenly throughout space. Obviously, the universe isn't uniform on small scales. We have planets, stars, galaxies, clusters of galaxies. Matter clumps together due to gravity. But according to the cosmological principle, if you zoom out far enough, if you look at scales of hundreds of millions or billions of light-years, the universe should start to look smooth and uniform. There shouldn't be any preferred directions. There shouldn't be any giant structures that stand out dramatically from the background. The cosmological principle isn't just some random assumption. It's based on observations and is fundamental to our models of how the universe formed and evolved. The cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform across the sky. Yes, there are tiny fluctuations, but they're incredibly small. Those tiny fluctuations grew over billions of years to form the galaxies and galaxy clusters we see today. But according to the math, according to the physics, there hasn't been enough time since the Big Bang for structures as large as the giant arc to form. There's actually a theoretical limit to how large structures in the universe can be. It's called the cosmological principle's scale limit, and it's around 1.2 billion light-years. Structures larger than this shouldn't exist because there simply hasn't been enough time for gravity to pull together that much matter over such vast distances. The giant arc, at 3.3 billion light-years, is nearly 3 times larger than this theoretical maximum. The Big Ring, at 1.3 billion light-years, is right at the edge or slightly beyond it. So how do we explain this? How can these structures exist if they violate our theoretical predictions? Several possibilities have been proposed, each with profound implications. First, maybe our understanding of the cosmological principle needs revision. Maybe the universe isn't as homogeneous on large scales as we thought. Maybe there's more large-scale structure than our current models predict. This would require significant changes to cosmological theory. But it wouldn't necessarily break everything. It would just mean the universe is lumpier on large scales than we expected. Second, maybe these structures aren't actually structures in the traditional sense. Maybe they're statistical flukes, random alignments of galaxies that happen to look like coherent structures from our perspective, but aren't actually gravitationally bound together. Imagine looking at stars in the night sky. From Earth, they form constellations, patterns that look meaningful. But those stars aren't actually related to each other. They're at vastly different distances. They only appear connected from our particular vantage point. Maybe the giant arc and Big Ring are similar illusions, 3-dimensional structures that look like 2-dimensional patterns due to projection effects. but astronomers have checked for this possibility extensively. They've analyzed the distances to the galaxies in these structures. They've looked at the velocities. They've examined whether these could be chance alignments. And while we can't rule it out completely, the evidence suggests these are real structures, not random alignments. The galaxies in these regions do seem to be associated with each other in ways that suggest genuine physical connections. Third, maybe there's something about the early universe we don't understand. Maybe there were processes occurring shortly after the Big Bang that could create larger structures than our current models predict. Maybe there were unusual density fluctuations in certain regions. Maybe dark matter behaved differently in the early universe. Maybe something about inflation, the rapid expansion that occurred fractions of a second after the Big Bang, created conditions that allowed larger structures to form. The truth is, we don't have a definitive answer yet. The giant arc and Big Ring are recent discoveries. They're still being studied intensively. More data is being collected. More analysis is being performed. And they're not the only large structures that have raised eyebrows among cosmologists. There are other examples of unexpectedly large structures in the universe, like the Hercules Corona Borealis Great Wall, another massive structure that challenges our theoretical expectations. What's clear is that these discoveries are telling us something important about the universe. Either our observations are missing something, or our theories need updating, or both. And that's how science progresses. We make observations. We develop theories to explain those observations. Then we make new observations that don't fit the theories. And we have to figure out what needs to change. Now, let's talk about the opposite extreme. Not a place where there's too much structure, but a place where there's almost nothing at all. It's called the Bootes Void, and it's one of the most eerily empty regions of space we've ever discovered. Imagine a sphere about 330 million light-years in diameter. For comparison, our entire Milky Way galaxy is only about 100,000 light-years across. So this void is thousands of times larger than our galaxy. It's a volume of space so enormous that you could fit thousands upon thousands of galaxies inside it. And yet, when astronomers look at the Bootes Void, they find almost nothing there. Only about 60 galaxies, in a space that should contain thousands upon thousands of them based on the average density of the universe. The void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were conducting a survey of galaxy redshifts, measuring how fast galaxies are moving away from us due to the expansion of the universe. And they noticed something strange. In the direction of the constellation Bootes, there was a huge region where they couldn't find any galaxies. At first, they thought it might be an observational error. Maybe there was something blocking their view. Maybe dust clouds were obscuring the galaxies behind them. But further observations confirmed what they were seeing. There really was an enormous region with very few galaxies. Now, to be clear, the Bootes Void isn't completely empty. There are some galaxies there. About 60 have been found, though that number might increase as we conduct more sensitive surveys. But 60 galaxies in a space this enormous is remarkably sparse. In a typical region of space this size, you'd expect to find around 2,000 galaxies or more. The void contains only about 3% of the expected number of galaxies. It's not completely empty, but it's close enough to empty that it raises fascinating questions. How do voids form? Why are there regions of space with so few galaxies? The answer lies in the early universe and the way structure formed after the Big Bang. Remember those tiny fluctuations in the cosmic microwave background I mentioned earlier? Those represent tiny variations in density in the early universe. Some regions had slightly more matter. Some regions had slightly less. Gravity amplified these differences over time. Regions with slightly more matter attracted even more matter, growing denser and denser, eventually forming galaxies and galaxy clusters. Regions with slightly less matter lost what little matter they had as it was gravitationally attracted to denser regions nearby. Over billions of years, this process created a cosmic web-like structure. Galaxies formed along filaments and nodes where matter concentrated. Between these filaments are voids, regions where matter was pulled away, leaving behind vast empty spaces. So voids are a natural consequence of structure formation in the universe. They're not strange in principle. What makes the Botez void particularly interesting is its size and emptiness. It's one of the largest known voids, and it's remarkably empty even compared to other voids. The few galaxies that do exist within it tend to be unusual. Many of them are smaller than typical galaxies. Some appear to be evolving differently from galaxies in denser environments. This makes sense when you think about it. Galaxy formation and evolution are influenced by environment. In dense regions, galaxies interact with each other. They collide and merge. Gas from the intergalactic medium funnels into them, fueling star formation. But in voids, galaxies are isolated. They don't interact with neighbors because there are no nearby neighbors. They can't acquire new gas easily, so they evolve more slowly, more quietly, undisturbed by the cosmic hustle and bustle that affects galaxies in denser regions. Studying voids like the Botez void helps us understand cosmology and structure formation. They tell us about the distribution of dark matter, the mysterious invisible substance that makes up most of the matter in the universe. They tell us about dark energy, the even more mysterious force causing the universe's expansion to accelerate. Voids are sensitive to cosmological parameters in ways that overdense regions aren't, so they provide unique tests of our theories. But there's also something profoundly unsettling about voids, something that strikes at a deep, almost philosophical level. The Botez void represents a volume of space so vast that if you were somehow transported to a galaxy in the center of it, the night sky would look completely different from what we see on Earth. There would be almost no galaxies visible in any direction. The universe would appear almost empty. You'd be surrounded by darkness, with only the faintest smudges of light indicating that anything else exists in the cosmos. From our perspective on Earth, we're in a relatively dense part of the universe. We're part of a galaxy cluster called the Local Group. Nearby are other galaxy clusters forming the Virgo supercluster. The night sky, at least through powerful telescopes, is full of galaxies in every direction. But from a galaxy in the Botez void, the universe would seem lonely, desolate, almost empty. It's a reminder of how much the universe varies from place to place, and how our understanding of it depends on where we happen to be located. The cosmic microwave background cold spot and Przybylski's star. Let me tell you about something that cosmologists have been puzzling over for about 2 decades now. It's called the CMB cold spot, and it's an anomaly in what should be one of the most uniform and well-understood signals in the entire universe. The cosmic microwave background radiation, or CMB for short, is the afterglow of the Big Bang itself. It's light that has been traveling through space for nearly 13.8 billion years, ever since the universe cooled enough for atoms to form and light to travel freely. The CMB is everywhere. No matter where you point your telescope, you can detect it. It's remarkably uniform in temperature, about 2.7 degrees above absolute zero. This uniformity is actually one of the most important pieces of evidence supporting the Big Bang theory. It shows that the early universe was incredibly smooth and homogeneous, exactly as the theory predicts. But the CMB isn't perfectly uniform. There are tiny temperature variations, tiny fluctuations from point to point. These fluctuations are incredibly small, only about 1 part in 100,000. But they're crucially important because they represent the seeds of all structure in the universe. Those slightly warmer spots were regions with slightly more matter. Those slightly denser regions eventually collapsed under gravity to form galaxies and galaxy clusters. The slightly cooler spots were regions with slightly less matter, which became the voids we just discussed. Scientists have mapped the CMB in extraordinary detail, using satellites like COBE, WMAP, and most recently, Planck. These maps show the temperature variations across the entire sky with incredible precision. And for the most part, everything matches theoretical predictions beautifully. The fluctuations have exactly the pattern we expect from the early universe. Their sizes, their distribution, their statistical properties all match what cosmological models predict almost perfectly. except for one spot, one particular region that doesn't fit, the CMB cold spot. This anomaly was first noticed in data from the Oumuamua satellite in 2003. It's a region about 5 degrees across on the sky, which might not sound like much, but remember, 5 degrees is about 10 times the width of the full moon. That's actually quite large in astronomical terms. And in this region, the CMB is significantly colder than it should be. We're talking about 70 microkelvin colder than the surrounding average temperature. That might sound tiny, and in absolute terms it is. But in the context of CMB fluctuations, where everything is supposed to be incredibly uniform, this is a massive anomaly. When scientists first saw it, they thought it might be a measurement error, so they checked everything. They looked for instrumental problems. They examined whether cosmic rays or other interference could have created a false signal. But when the Planck satellite, a more advanced instrument launched years later, mapped the same region, the cold spot was still there. It's real. It's actually out there in the cosmos. So, what could cause such a large cold region in the CMB? Several theories have been proposed, ranging from the mundane to the genuinely exotic. The first and most straightforward explanation is that it's just a statistical fluke. If you have enough random data points, occasionally you'll get clustering that looks unusual purely by chance. Imagine flipping a coin 1,000,000 times. You'd expect roughly equal numbers of heads and tails overall. But somewhere in that million flips, you might find a stretch of 20 heads in a row purely by random chance. Maybe the cold spot is similar, just an unusually large fluctuation that happened randomly. The problem with the statistical fluke explanation is probability. Scientists have calculated the odds of such a large anomaly appearing by pure chance. The numbers vary depending on exactly how you do the calculation, but generally, the cold spot is unusual enough that it should only occur by random chance in about 1 or 2% of universes. That's not impossible, certainly. We might just be in one of the unlucky universes that got a weird statistical fluctuation. But it's unlikely enough that scientists want to explore other possibilities. One intriguing idea is that the cold spot might be caused by a supervoid. Remember our discussion of the Boötes void? Well, if there's a particularly large and empty void between us and the CMB in that direction, it could create a cold spot through something called the integrated Sachs-Wolf effect. This is a complex phenomenon, but here's the basic idea. As CMB photons travel through a void, they lose a tiny amount of energy climbing out of the void's gravitational potential. If the void is expanding as the photons pass through it, which it would be in our expanding universe, they lose a bit more energy. This energy loss makes the photons slightly cooler, creating a cold spot in the CMB in that direction. Astronomers have indeed found evidence for a large void in the direction of the cold spot. Studies have shown that there's a region with fewer galaxies than expected along that line of sight. But here's the problem. The void they've found doesn't appear to be quite large enough or quite empty enough to fully explain the magnitude of the cold spot. The numbers don't quite add up. The void might contribute to the anomaly, but it probably can't explain all of it by itself. And then there are more exotic explanations. Some cosmologists have suggested the cold spot might be evidence of a collision between our universe and another universe in the multiverse. According to some versions of eternal inflation theory, our universe might be one of many bubble universes existing in a larger multiverse. If our universe collided with another universe in the very early stages, shortly after the Big Bang, it would leave a signature in the CMB. That signature might look like an unusually cold or hot spot. It's a genuinely fascinating idea, but it's also highly speculative. We have no independent evidence for other universes, and testing this hypothesis is extraordinarily difficult. Another exotic possibility is that the cold spot is evidence of a topological defect in space-time. In the very early universe, as it cooled and underwent phase transitions, defects might have formed, similar to cracks forming in ice. These cosmic defects could include things called cosmic strings or cosmic textures. If one of these happened to be in the direction of the cold spot, it could potentially create the observed anomaly. Again, this is highly speculative. We've never definitively detected a cosmic defect, though we continue to search for them. As of 2025, the CMB cold spot remains unexplained. It's probably not a measurement error, because multiple independent observations have confirmed it. It might be a statistical fluke, but that seems somewhat unlikely given the probabilities involved. It might be partially explained by a supervoid, but probably not entirely. And it might be evidence of exotic physics, though we'd need much more evidence to take that seriously. What makes this particularly frustrating is that we can't get more data easily. The CMB is a one-time snapshot of the universe when it was about 380,000 years old. We can map it in more detail, which we've done with successive satellite missions, but we can't see behind it or through it. It's an opaque wall, a cosmic horizon beyond which we cannot directly observe. So the cold spot sits there in the data, a puzzling anomaly in what should be a smooth and well-understood signal, challenging our understanding and reminding us that the universe still holds surprises. Now let's shift gears completely and talk about something on a much smaller scale, but equally puzzling in its own way. A single star that contains things it absolutely should not contain. It's called Przybylski's star, named after the astronomer Antoni Przybylski, who first studied it in detail in 1961. And it has left stellar physicists scratching their heads for more than 60 years. Przybylski's star is located about 370 light-years from Earth in the constellation Centaurus. It's what we call a spectroscopic peculiar star, which is scientific code for this star's light spectrum looks really weird and we don't fully understand why. When you split a star's light into its component colors, its spectrum, you can identify which elements are present in the star's atmosphere based on the absorption lines. Different elements absorb light at specific wavelengths, creating a unique fingerprint. For most stars, the spectrum shows what you'd expect. Lots of hydrogen, the most abundant element in the universe. Significant helium, the second most abundant element. Smaller amounts of heavier elements like carbon, oxygen, nitrogen, iron. The exact proportions vary depending on the star's age and composition, but they generally make sense based on our understanding of stellar physics and nucleosynthesis, the process by which stars create elements through nuclear fusion. Przybylski's star doesn't follow this pattern, not even close. Its spectrum shows unusual abundances of rare Earth elements, elements like holmium, ytterbium, strontium, californium. Some of these elements are incredibly rare in normal stellar atmospheres. And here's the truly bizarre part. Przybylski's star appears to contain technetium and promethium, and possibly even heavier radioactive elements. Why is this a problem? Because technetium and promethium don't exist naturally on Earth for any significant length of time. They're radioactive. Technetium's longest-lived isotope has a half-life of about 4 million years. Promethium's longest-lived isotope has a half-life of less than 18 years. These are incredibly short timescales in astronomical terms. Stars live for millions or billions of years. Przybylski's star is estimated to be somewhere around several billion years old. So if the star contains technetium or promethium, and those elements decay away in mere millions of years or even less, that means the star must be actively producing them right now. But we don't understand how or why. Normal stellar fusion processes occur in the star's core, not in the visible surface layers where we detect these elements. And the fusion processes we know about don't preferentially create these particular radioactive elements in the proportions we observe. Several theories have been proposed to explain Przybylski's star and similar chemically peculiar stars. One idea involves what we call atomic diffusion. In some stars, particularly those with very stable atmospheres and low levels of mixing, elements can separate based on their atomic properties. Heavier elements can sink toward the star's interior, while lighter elements float to the surface, or vice versa under certain conditions. This process could concentrate rare elements in the visible surface layers of the star, making them appear much more abundant than they actually are overall. But atomic diffusion doesn't easily explain the presence of short-lived radioactive elements. Even if diffusion concentrated them at the surface, they still have to come from somewhere. They still have to be created somehow. And if they're being created deep in the star's core and then transported to the surface, that transportation would need to happen very quickly, much faster than normal stellar processes typically work. Another possibility is that the star is capturing material from its environment. Maybe there's a companion object we haven't detected, perhaps a planet or smaller star that's being torn apart by tidal forces. As this material falls onto Przybylski's star, it could alter the composition of the star's outer layers. Some unusual nuclear processes might occur as this material accretes, potentially creating the observed element. But this raises more questions than it answers. What kind of companion object would have the right composition? How would the accretion process create these specific elements? And if this explanation is correct, why don't we see more stars like Przybylski's star? Accretion should be fairly common in binary star systems. Some scientists have proposed more exotic explanations. Perhaps there are nuclear processes occurring in the star's outer layers that we don't understand. Maybe magnetic fields play a role, creating conditions that allow unusual nuclear reactions. Maybe the star's rotation and magnetic field work together to dredge up material from deeper layers faster than we'd normally expect. There's even been semi-serious speculation about truly exotic possibilities. In the 1970s, some scientists half-jokingly suggested that maybe Przybylski's star is surrounded by the radioactive waste dumps of an alien civilization. If an advanced society had been using nuclear fission or breeding radioactive isotopes for some purpose, and then dumped the waste products around their star, we might detect the signature of those elements in the star's spectrum. This is obviously highly speculative and almost certainly wrong, but it shows how puzzling this star truly is when even serious scientists start considering alien waste dumps as potential explanations. As of now, Przybylski's star remains unexplained. We continue to study it. We've found a few other stars with somewhat similar properties, though none quite as extreme. These chemically peculiar stars tell us that our understanding of stellar physics is incomplete. There are processes occurring in some stars that we don't fully comprehend yet. Maybe it's unusual mixing mechanisms. Maybe it's exotic nuclear processes. Maybe it's something we haven't even thought of. What's clear is that the universe produces stars in more varieties than our theories initially predicted. Most stars are well-behaved and match our models beautifully. But every so often, we find oddities, like Przybylski's star, that remind us how much we still have to learn. These peculiar objects are incredibly valuable scientifically because they push the boundaries of our knowledge. They force us to think harder, to come up with new ideas, to expand our theories, to account for observations that don't fit neatly into our current understanding. Interstellar visitors and fast blue optical transients. In October of 2017, something extraordinary happened. For the first time in human history, we detected an object passing through our solar system that came from interstellar space. An actual visitor from another star system. The object was discovered by the Pan-STARRS telescope in Hawaii and was given the Hawaiian name Oumuamua, which roughly translates to scout or messenger from afar arriving first. And this messenger turned out to be one of the strangest objects we've ever observed. Oumuamua's trajectory immediately told astronomers it was something special. When you plot the orbit of an object in our solar system, whether it's a planet, asteroid, or comet, it follows an ellipse or circle around the sundial. But Oumuamua's trajectory was hyperbolic. It came from outside the solar system, swung around the sun, picking up speed, and headed back out into interstellar space, never to return. Based on its trajectory, astronomers could trace back where it came from. It appeared to originate from the general direction of the star Vega, though it would have taken so long to travel that distance that Vega wasn't actually in that position when Oumuamua began its journey. We only detected Oumuamua because it happened to pass relatively close to Earth. By the time we spotted it, it was already leaving the solar system. Astronomers had a very limited window to observe it before it became too faint and too distant for even our best telescopes to see. During that brief observation period, they learned some genuinely weird things about this object. First, its shape appeared to be highly unusual. Based on how its brightness changed as it tumbled through space, astronomers calculated that Oumuamua is probably elongated, perhaps cigar-shaped or pancake-shaped. The estimates suggest it might be about 400 meters long, but only about 40 meters wide. That's an aspect ratio of 10:1, much more elongated than any asteroid or comet we've seen in our solar system. Most natural objects are relatively spherical or only moderately elongated due to the way gravity works. Finding something this stretched out was genuinely surprising. Second, Oumuamua accelerated slightly as it moved away from the Sunday now. That might not sound strange at first. After all, comets accelerate as they approach the Sun due to the rocket-like effect of gases venting from their surfaces when the ice heats up. But here's the thing. Oumuamua showed no signs of being an active comet. There was no visible tail, no coma of gas and dust surrounding it. Telescopes looked carefully for any evidence of outgassing and found essentially nothing. Yet it was accelerating anyway. This acceleration wasn't huge. It was small, subtle, right at the edge of what we could measure. But it was definitely real and statistically significant. Something was pushing Oumuamua, giving it a little extra speed as it moved away from the Sunday. But what? Scientists proposed several explanations for this anomalous acceleration. The most straightforward is that Oumuamua is a comet after all, but one that's outgassing in ways we couldn't easily detect. Maybe it's venting pure hydrogen, which would be nearly invisible to our instruments. Maybe the outgassing is happening from small areas that we couldn't resolve with our telescopes. Maybe its composition is unusual in ways that make the outgassing very subtle. This remains the leading natural explanation in the scientific community. But there are problems with the hydrogen outgassing hypothesis. For it to work, Oumuamua would need to be almost entirely made of hydrogen ice. We don't know of any process that would create such an object. And if it were made of hydrogen ice, it probably wouldn't survive the journey through interstellar space. Cosmic rays and ultraviolet starlight would evaporate it over the millions of years it's been traveling. Another idea is that Oumuamua is a light sail, either natural or artificial. A light sail is an extremely thin sheet that's pushed by the pressure of sunlight. If Oumuamua is pancake-shaped rather than cigar-shaped, and if it's very thin and light, then the pressure of sunlight could account for the observed acceleration. Some scientists, most notably Harvard astronomer Avi Loeb, have suggested that Oumuamua might be an artificial light sail created by an alien civilization. Perhaps it's a probe deliberately sent to explore the galaxy. Or perhaps it's the derelict remains of alien technology, tumbling through space long after its creators are gone. The artificial hypothesis is fascinating and has generated enormous public interest. But most scientists are skeptical, not because we can prove it's wrong, but because artificial origins require extraordinary evidence, and what we observed from Oumuamua, while unusual, can potentially be explained by natural processes we don't fully understand yet. When you find something strange, the first step is always to exhaust natural explanations before jumping to artificial ones. Other theories suggest Oumuamua might be a fragment of a planet destroyed when its star went supernova, compressed into a dense, unusual form by the explosion. Or maybe it's a type of object that's common in interstellar space, but we've just never seen before because we've never had the sensitivity to detect interstellar visitors until now. Perhaps interstellar space is full of Oumuamuas, and we're only now developing the technology to spot them. Then in August 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor, now called Comet Borisov, or 2I/Borisov in astronomical nomenclature. Unlike Oumuamua, Borisov looked like a fairly normal comet. It had a visible coma, a fuzzy cloud of gas and dust. It had a tail. It was outgassing visibly as the sun heated its icy surface. Its composition, based on spectroscopic analysis, seemed similar to comets from our own solar system. It was reassuringly normal. Borisov's discovery was important for several reasons. First, it confirmed that interstellar objects do pass through our solar system occasionally. Oumuamua wasn't a one-time fluke. Second, it showed that at least some interstellar objects are normal comets, similar to what we have in our own solar system. This makes sense theoretically. During the formation of planetary systems, lots of material gets ejected into interstellar space. Some of that material should be icy comets. Every star system probably produces countless comets, and some fraction of them get kicked out into the galaxy. The fact that Borisov looked normal actually made Oumuamua seem even stranger by comparison. If interstellar objects are typically normal comets like Borisov, then what exactly is Oumuamua? Why is it so different? Is it rare, or are there many different types of interstellar objects, and we've just seen a tiny, non-representative sample so far? Astronomers estimate that several interstellar objects probably pass through the inner solar system every year. But most of them go undetected because they're small and faint, and we're not looking in the right direction at the right time. As survey telescopes become more powerful and scan more of the sky more frequently, we'll detect more of these visitors. Each one will give us a glimpse of other star systems, a sample of the material that exists in the broader galaxy beyond our solar system's boundaries. The Vera C. Rubin Observatory, which began operations recently, is expected to detect many interstellar objects over the coming years. With its large mirror and wide field of view, it will scan the entire visible sky repeatedly, spotting faint, fast-moving objects that previous surveys would have missed. We're entering an era where studying interstellar visitors will become a regular part of astronomy rather than a rare, extraordinary event. These objects are scientifically valuable because they're samples from other stellar systems delivered to our doorstep. We don't have to travel light years to study material from other stars. It comes to us. Each interstellar visitor carries information about its origin. Its composition tells us what materials were present in the planetary system where it formed. Its trajectory tells us about the dynamics of that system, how objects were ejected and sent wandering through the galaxy. By studying many interstellar objects, we can start to understand what's typical and what's unusual among planetary systems in our galactic neighborhood. And who knows, maybe one day we'll detect an interstellar visitor that's genuinely artificial, a probe sent by another civilization, deliberately designed to explore the galaxy. Or maybe we'll find something even stranger than Oumuamua, something that challenges our understanding even more profoundly. The universe has shown repeatedly that it's capable of surprising us. Every time we develop new capabilities, new instruments, new ways of observing the cosmos, we find things we didn't expect. Now let me tell you about something that's happening much farther away, but equally mysterious in its own right. In recent years, astronomers have discovered a new class of cosmic explosions that shouldn't exist according to our understanding of stellar death. They're called fast blue optical transients, or FBOTs for short, and they're genuinely bizarre. We've known about stellar explosions for a long time. Supernovae have been observed for centuries. We understand the basic physics behind most types of supernovae. When a massive star runs out of fuel, its core collapses catastrophically, and the outer layers are blown off in an enormous explosion. Or in a different scenario, a white dwarf star accumulates too much material from a companion star, exceeds a critical mass limit, and detonates in a thermonuclear explosion. These explosions are bright, incredibly bright, outshining entire galaxies for brief periods. But they follow predictable patterns. Supernovae take days or weeks to reach peak brightness. They have characteristic light curves, graphs, showing how their brightness changes over time. They emit light in predictable colors and wavelengths. After decades of study, we've classified supernovae into various types based on their properties, and we understand most of them reasonably well. Fast blue optical transients don't fit these patterns. They're called fast because they brighten and fade incredibly quickly, reaching peak brightness in just a few days, and fading significantly within a week or two. They're called blue because they emit strongly in blue wavelengths of light, indicating extremely high temperatures. And they're called transients because they appear suddenly and disappear quickly, temporary phenomena rather than persistent objects. The first well-studied F-bot was discovered in 2018 and given the informal name the Cow because its official designation, AT2018 Cow, happened to end in those letters. The Cow appeared in a galaxy about 200 million light-years away. It brightened incredibly rapidly, reaching peak luminosity in just 2 days. At its peak, it was about 100 times brighter than a typical supernova. Then it faded quickly, dropping by half in brightness every few days. The Cow's spectrum was bizarre. It showed very broad emission lines, indicating material moving at tremendous speeds, over 30,000 kilometers per second. That's 10% of the speed of light. It was also emitting high-energy X-rays and radio waves, signatures we don't typically see from normal supernovae, at least not in the same combination and intensity. Astronomers scrambled to observe the Cow with every available instrument. They pointed X-ray telescopes, radio telescopes, optical telescopes, all at this one object, trying to figure out what it was. And they came up with several theories, each attempting to explain this bizarre explosion. Maybe it was a failed supernova. Perhaps a massive star tried to explode, but the core collapse created a black hole that swallowed most of the explosion's energy, leaving only a brief, bright flash visible. Or maybe it was a star being torn apart by a black hole in what's called a tidal disruption event. When a star gets too close to a black hole, tidal forces rip it apart, and the debris falling into the black hole can produce brilliant flares of light. Another theory suggested the Cow might be the birth of a neutron star, or black hole, witnessed in real time. When a massive star's core collapses, it can form a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Or if the core is massive enough, it forms a black hole. Maybe what we're seeing with F-bots is the actual moment of formation, the first light from these newborn compact objects. Since the Cow, astronomers have discovered several more F-bots. Each one is slightly different, but they share common features: rapid brightening and fading, blue colors indicating high temperatures, high velocities indicated by broad spectral lines, unusual multi-wavelength emissions. They seem to be relatively rare, much rarer than regular supernovae, but not exceptionally rare. We're finding a few per year now that we know what to look for. One particularly interesting FBOT was discovered in 2020 and nicknamed the Camel. This one was even more extreme than the Cow. It brightened faster, reached higher peak luminosity, and showed even more unusual properties. The more F-bots we discover, the more diverse they appear to be. They're not all identical. They form a class of phenomena with variations, suggesting perhaps multiple physical mechanisms can produce similar-looking events. The challenge with studying FBOTs is their speed. They appear suddenly and fade quickly. By the time you notice one and get telescopes pointed at it, it might already be fading. You need fast response capabilities, automated systems that can detect transients and immediately alert astronomers, robotic telescopes that can slew to the position within minutes. The modern era of time-domain astronomy, where we monitor the sky for things that change or appear suddenly, is making F-bot studies possible. What do FBOTs tell us? First, they reveal that stellar death is more diverse and complex than we thought. We don't have a complete catalogue of everything that can happen when stars explode or when compact objects are born. There are still surprises waiting for us. Second, they show that extreme physics produces observable signatures. Whatever is happening in F-bots involves tremendous energy being released very quickly from a very small region. That means extreme temperatures, extreme densities, extreme magnetic fields, conditions that we can't replicate in laboratories on Earth. By studying FBOTs, we learn about physics under the most extreme conditions nature provides. Third, F-bots might be connected to other mysterious phenomena. Some scientists think they might be related to certain types of gamma-ray bursts, brief flashes of extremely high-energy radiation that we detect from distant galaxies. Or they might be related to mysterious radio signals or other transient phenomena we don't fully understand. The universe is full of brief, energetic events, and figuring out which ones are related and which are distinct phenomena is an ongoing challenge. As our survey capabilities improve, we'll detect more F-bots, we'll gather more data, we'll test theories against observations. Eventually, we'll figure out what causes these bizarre explosions. But for now, they remain mysterious. They're one more reminder that when we look at the universe with new eyes, using new instruments and new techniques, we find things we didn't expect. The cosmos is far stranger and more diverse than our theories initially predict. The Methuselah Star and conclusion. Let me tell you about a star with a problem, a big problem. This star appears to be older than the universe itself. Obviously, that's impossible. Nothing can be older than the universe, because nothing existed before the universe began. So either our measurement of the star's age is wrong, or our measurement of the universe's age is wrong, or something about our understanding is fundamentally flawed. This is the paradox of the Methuselah Star, officially designated HD 140283. The star is named after Methuselah, the biblical figure who supposedly lived for 969 years, making him the longest-lived person in the Bible. HD 140283 is named Methuselah because it's one of the oldest known stars in our galaxy. And when scientists first calculated its age, they got a result that was deeply problematic. The star appeared to be about 16 billion years old, but the universe itself is only 13.8 billion years old. That's a problem. How do astronomers determine the age of a star? There are several methods, but for very old stars like Methuselah, the primary technique involves studying the star's composition and comparing it to theoretical models of stellar evolution. When we look at a star's spectrum, we can determine what elements it contains and in what proportions. Young stars, formed recently from gas enriched by previous generations of stars, contain significant amounts of heavy elements like iron, carbon, oxygen, and others. Old stars, formed when the universe was younger and fewer generations of stars had lived and died, contain much less of these heavy elements. Methuselah has very low metallicity, using the astronomical term where metals means any element heavier than hydrogen and helium. This low metallicity immediately tells us it's old, formed in the early universe before much chemical enrichment had occurred. By comparing its composition and other properties to theoretical models of how stars evolve over time, astronomers can estimate its age. The initial estimates from the early 2000s suggested Methuselah was about 16 billion years old, with an uncertainty range that still placed it older than the universe. This created what's called an age crisis. How could a star be older than the universe? Something had to be wrong. Several factors contribute to the uncertainty in age measurements. First, the star's distance matters. If the star is closer than we think, it's actually intrinsically dimmer, which would make it older. If it's farther than we think, it's intrinsically brighter, which would make it younger. Measuring distances to stars is challenging. For nearby stars, we use parallax, the apparent shift in position as Earth orbits the Sunday. But even with precise instruments, parallax measurements have uncertainties. Second, the star's chemical composition affects the calculation. Even small changes in the assumed abundance of certain elements can shift the age estimate by hundreds of millions or even billions of years. Third, the theoretical models of stellar evolution have their own uncertainties. We input the star's mass, composition, and other properties into computer models that simulate how the star evolves over time. But these models depend on our understanding of nuclear physics, heat transport, and other processes. Uncertainties in the physics translate to uncertainties in the age. As better data became available, particularly from the Hipparcos and later Gaia space missions, which measured stellar distances with unprecedented precision, the estimated age of Methuselah came down. The current best estimate places it at around 13.7 billion years, with an uncertainty of plus or minus zero point 0.7 billion years or so. That uncertainty range is crucial. It means the star could be as young as 13 billion years, or as old as 14.4 billion years. The universe's age is currently estimated at 13.8 billion years, with an uncertainty of about plus or minus 0.02 billion years, based on measurements of the cosmic microwave background and other cosmological data. So within the uncertainties, Methuselah's age is now consistent with the universe's age. The star could be 13.5 billion years old, while the universe is 13.8 billion years old. Problem solved, right? Well, sort of. The uncertainties still overlap uncomfortably. If both the star and the universe happen to be at certain ends of their uncertainty ranges, the paradox returns. The star would again appear older than the universe. This makes astronomers nervous. It suggests we're right at the edge of our measurement capabilities, where small errors or systematic biases could lead to contradictory results. Moreover, Methuselah isn't the only very old star we've found. There are others with similarly extreme ages. If all of them were systematically measured too old, that might indicate a problem with our stellar age dating methods. Or if the universe is systematically measured too young, that might indicate a problem with our cosmological models. Either way, these very old stars push the boundaries of our knowledge and test whether our methods are reliable. The existence of stars nearly as old as the universe itself does make sense theoretically. The first stars formed a few 100 million years after the Big Bang, once the universe had cooled enough for gas clouds to collapse under gravity. These first stars were made almost entirely of hydrogen and helium, the only elements created in the Big Bang itself. Some of them were massive and short-lived, exploding as supernovae within millions of years. But others were smaller, with masses similar to or less than our Sun. Those smaller stars can live for many billions of years. Methuselah is what's called a population 2 star. Part of the second generation of stars formed after the first generation enriched the universe with heavier elements. Even so, it contains very little in the way of heavy elements, indicating it formed very early. It's not quite a first-generation star, which we call population 3 stars, and have never definitively observed, but it's close. It's a relic from the early universe, still shining today, giving us a window into conditions billions of years ago. Studying ancient stars like Methuselah helps cosmologists understand the early universe. These stars were witnesses to cosmic history. They formed when the universe was young, when galaxies were just beginning to assemble, when conditions were dramatically different from today. By analyzing their composition, we learn about the chemical makeup of the early universe. By measuring their ages, we test our chronology of cosmic history. The fact that we found a star whose age is uncomfortably close to the universe's age is actually a good sign in a way. It means we're pushing our observational capabilities to the limit. We're measuring things at the edge of what's possible. And at those edges, we find tensions and puzzles that force us to improve our methods and refine our theories. If everything fit together perfectly with no puzzles or contradictions, it would almost be suspicious. It would suggest we're not looking hard enough. So where does that leave us with Methuselah? As of 2025, the best measurements are consistent with the star being slightly younger than the universe, though the margins are tight. Future missions like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will provide even better data. We'll measure distances more precisely. We'll analyze stellar spectra in more detail. We'll refine our models of stellar evolution. Gradually, the uncertainties will shrink, and we'll know with greater confidence whether stars like Methuselah pose a genuine problem or whether the apparent paradox is just an artifact of measurement uncertainties. But even if the technical paradox is resolved, Methuselah remains a remarkable object, a star that has been burning for nearly the entire history of the universe, a star that formed when our galaxy was young and unstructured, a star that has witnessed the entire epic story of cosmic evolution from a universe of mostly hydrogen and helium to a universe rich with planets, life, and complexity. It's still there, still shining, a testament to the incredible timescales involved in cosmic history. Now, as we approach the end of our journey through these cosmic mysteries, let's step back and think about what all of these phenomena tell us collectively. What's the bigger picture here? What do we learn from the WOW signal, from Tabby's star, from odd radio circles, from giant cosmic structures, from cosmic voids, from the CMB cold spot, from Przybylski's star, from Oumuamua, from fast blue optical transients, and from ancient stars like Methuselah? The first and most important lesson is humility. We've been studying the universe scientifically for only a few centuries. Modern astronomy with sophisticated instruments has existed for less than 100 years. Radio astronomy began in the 1930s. Space telescopes only became possible in the latter half of the 20th century. We're incredibly young in our journey of cosmic exploration. And yet, in that brief time, we've discovered that the universe is far stranger, far more complex, and far more diverse than anyone imagined. Every time we develop a new observational capability, we find surprises. When we first turned radio telescopes toward the sky, we discovered pulsars, objects so bizarre that astronomers initially wondered if they might be alien beacons. When we launched X-ray telescopes above Earth's atmosphere, we found black holes actively feeding on matter, creating brilliant beams of radiation. When we built gravitational wave detectors, we detected colliding black holes and neutron stars, confirming predictions of general relativity, while also revealing that these mergers are more common than expected. The mysteries we've discussed today are recent additions to a long list of things we didn't expect to find. Some of them will likely be explained by natural processes we already understand, just applied in unusual circumstances. The WOW signal might turn out to be a comet or some other natural radio source. Tabby's star might be explained by a debris field from a planetary collision. Odd radio circles might be shock waves from galactic explosions. The CMB cold spot might be a statistical fluke or a supervoid. Przybylski's star might have unusual mixing processes we don't fully grasp yet. Oumuamua might be a hydrogen iceberg or a fragment of a shattered planet. Fast blue optical transients might be a specific type of stellar explosion. The Methuselah star might simply be at the young end of its uncertainty range. But here's the crucial point. Even if all of these mysteries are eventually explained by conventional physics, the fact that they surprised us is significant. It tells us that our understanding, while extensive, is incomplete. We have the basic framework right. The laws of physics work. Our theories describe reality reasonably well. But the universe is so vast, so old, so complex, that it keeps finding ways to arrange matter and energy that we haven't thought of yet. It keeps producing phenomena at the edges of our theoretical predictions, in regimes we haven't fully explored, under conditions we can't replicate in laboratories. The second lesson is about the nature of scientific inquiry itself. Notice that for each of these mysteries, scientists have proposed multiple explanations. They haven't jumped to single conclusions. They've considered various possibilities, weighed evidence, calculated probabilities, and remained honestly uncertain where uncertainty exists. This is how science is supposed to work. When you encounter something unexplained, you don't immediately claim to know the answer. You propose hypotheses, you gather more data, you test predictions. You remain open to multiple possibilities until the evidence decisively supports one over the others. This process can be frustrating for people who want definitive answers immediately. It's tempting to hear about Tabby's star and conclude, it's aliens, because that's exciting. It's tempting to hear about the WOW signal and declare, we found extraterrestrial intelligence, because that would be momentous. But science requires patience and rigor. Extraordinary claims require extraordinary evidence. The possibility of aliens or exotic physics or revolutionary discoveries must be weighed against more mundane explanations that fit within our current understanding. That doesn't mean scientists are close-minded or unwilling to consider radical ideas. quite the opposite. If genuine evidence for alien technology or physics beyond the standard model, or violations of the cosmological principle emerged, the scientific community would ultimately accept it. But the burden of proof is high, as it should be. We've learned through centuries of experience that most surprising observations turn out to have natural explanations consistent with known physics, even if those explanations weren't immediately obvious. The third lesson is about the tools we use to explore the universe. Almost every mystery we've discussed was discovered because we developed new observational capabilities. The WOW signal was detected by radio telescopes that didn't exist before the mid-20th century. Tabby's star's bizarre dimming was discovered by the Kepler space telescope's incredibly precise photometry. Odd radio circles were found by a new generation of radio telescope arrays. The giant cosmic structures and the Botez void emerged from large-scale surveys mapping millions of galaxies. The CMB cold spot appeared in detailed maps of the cosmic microwave background. Przybylski's star's unusual composition was revealed by spectroscopic analysis. Oumuamua was spotted by Pan-STARRS, a telescope designed to scan for near-Earth objects and transients. Fast blue optical transients are being discovered by surveys that repeatedly image the entire sky looking for things that change. The Methuselah star's extreme age was calculated using data from space missions measuring stellar distances with extraordinary precision. This pattern is no coincidence. New instruments reveal new phenomena. As we build larger telescopes, more sensitive detectors, broader surveys, and more sophisticated analysis techniques, we inevitably find things we didn't know existed, and that trend will continue. The Vera C. Rubin Observatory will scan the sky night after night for 10 years, generating an enormous database of changing and transient phenomena. The square-kilometer array, when completed, will be the most sensitive radio telescope ever built, orders of magnitude more capable than current instruments. The James Webb Space Telescope is already showing us the early universe in unprecedented detail. The Nancy Grace Roman Space Telescope will map millions of galaxies to understand dark energy and cosmic structure. Each of these new facilities will almost certainly discover unexpected phenomena. We can predict that with confidence because it's happened every single time we've built a more powerful instrument. We cannot predict what those phenomena will be. If we could, they wouldn't be unexpected. But we can be confident that the universe still holds surprises for us. There are still mysteries waiting to be discovered, things happening right now in the cosmos that we haven't even detected yet. The fourth lesson is about the sheer scale and diversity of the universe. Think about the range of phenomena we've discussed. Radio signals from interstellar space, stars that dim irregularly, circular radio structures hundreds of thousands of light-years across, cosmic structures billions of light-years long, voids spanning hundreds of millions of light-years containing almost nothing, anomalies in the primordial radiation from the Big Bang, individual stars with bizarre chemical compositions, visitors from other star systems, explosions that defy classification, stars almost as old as the universe itself. These phenomena span an incredible range of scales in both space and time, from individual stars a few hundred light-years away to structures spanning billions of light-years, from events lasting seconds to objects that have existed for billions of years. And these are just the things that happen to puzzle us currently. There are countless other cosmic phenomena that we understand better but are equally remarkable in their own ways. The universe contains at least 2 trillion galaxies in the observable volume alone. Each galaxy contains tens of billions to hundreds of billions of stars. Many of those stars have planets. Some of those planets are in habitable zones where liquid water could exist. The numbers are almost incomprehensible. And every one of those stars has a life cycle. Every galaxy has a history. Every cosmic structure formed through specific physical processes acting over cosmic time. Given this immense scale and complexity, it would be astonishing if we understood everything. It would be shocking if there were no mysteries, no puzzles, no phenomena that surprised us. The fact that we find unexplained things is exactly what we should expect. We're finite beings with finite lifespans and finite resources, trying to understand an essentially infinite cosmos. Of course, there are things we don't understand yet. Of course, the universe surprises us. The real miracle is that we understand as much as we do. The fifth lesson, and perhaps the most profound, is about the provisional nature of scientific knowledge. Everything we think we know about the universe is subject to revision in light of new evidence. Our current best theories, general relativity and quantum mechanics, and the standard model of particle physics, and the lambda CDM model of cosmology, are incredibly successful. They've made countless predictions that have been confirmed by observation and experiment. They describe reality with remarkable accuracy across an enormous range of conditions. But we also know these theories are incomplete. General relativity and quantum mechanics are mathematically inconsistent with each other, which means at least one of them must be modified when we eventually develop a theory of quantum gravity. The standard model doesn't include gravity and has other known limitations. The lambda CDM model requires dark matter and dark energy, neither of which we truly understand. We know what they do gravitationally, but we don't know what they actually are. So our current theories are the best we have, and they work extremely well within their domains of applicability. But they're not the final word. Future theories will almost certainly reveal that our current understanding, while largely correct, is a special case of something deeper and more comprehensive. This has happened before in the history of science. Newton's laws of motion and gravity were thought to be fundamental and universal. Then Einstein showed that they're actually approximations that work well at low speeds and weak gravitational fields, but break down under extreme conditions. Newton wasn't wrong exactly, but his theories were incomplete, limited cases of Einstein's more general framework. The same will likely happen to our current theories eventually. Some future physicist will develop new mathematics and new concepts that encompass general relativity and quantum mechanics as special cases. And in the process, phenomena that seem mysterious to us now might become clear and understandable within that new framework. The mysteries we've discussed today might play a role in that future understanding, or they might not. They might turn out to be explainable within current physics and simply require more data or more careful analysis. But the possibility exists that one of these anomalies, one of these strange observations that doesn't quite fit, contains a clue to deeper physics. That's why scientists take these mysteries seriously. That's why we keep studying them, keep gathering data, keep proposing and testing hypotheses. Throughout history, unexplained observations have sometimes led to major breakthroughs. The orbit of Mercury precessed slightly more than Newton's gravity predicted. This tiny discrepancy, only about 43 arc-seconds per century, seemed like a minor puzzle. But Einstein's general relativity explained it perfectly, and in the process, revolutionized our understanding of space, time, and gravity. The blackbody radiation spectrum, the specific way hot objects emit light, couldn't be explained by classical physics. Trying to explain it led Max Planck to propose that energy comes in discrete packets called quanta, launching the quantum revolution. Could the wow signal, or Tabby's star, or odd radio circles, or any of the other mysteries we've discussed be similar harbingers of a scientific revolution? Probably not. Most anomalies turn out to have conventional explanations. But we won't know until we investigate thoroughly. We won't know until we gather more data, develop better theories, and test our understanding against reality. And that brings us to perhaps the most important point of all. Science is a process, not a destination. It's an ongoing journey of discovery, characterized by curiosity, skepticism, rigorous testing, and honest acknowledgement of uncertainty. When scientists say we don't know, that's not a failure. That's honesty. That's intellectual integrity. That's an admission that the universe is complex and our understanding is limited, and more work needs to be done. The mysteries we've explored tonight are not frustrations or embarrassments for science. They're opportunities. They're invitations to look more carefully, think more deeply, develop better tools, and expand our understanding. They're reminders that for all we've learned, there's still so much more to discover. They're evidence that the universe is endlessly fascinating, capable of surprising us even after centuries of study. Each generation of scientists stands on the shoulders of previous generations, seeing a bit farther, understanding a bit more deeply. The astronomers of the 19th century didn't know about galaxies beyond the Milky Way. They thought the universe was static and eternal. Within 100 years, we'd discovered the expanding universe, the Big Bang, dark matter, dark energy, exoplanets, and countless other phenomena they couldn't have imagined. What will scientists 100 years from now know that we can't currently imagine? What will they think of our current mysteries? Will they look back at Tabby's star and odd radio circles and fast blue optical transients the way we look back at historical puzzles that have since been explained? Will they smile at our confusion, understanding clearly what we could only glimpse darkly? Or will some of these mysteries remain unsolved even then, perhaps joined by new mysteries we haven't discovered yet? Will future scientists still be debating the wow signal, still wondering if it was natural or artificial? Will they have found more interstellar visitors and determined whether Oumuamua was typical or exceptional? Will they have mapped the universe in such detail that structures like the giant arc and Big Ring make perfect sense? Or will those structures still challenge cosmological models? We can't know the answers to these questions, but we can be confident that the journey of discovery will continue. Humans are curious by nature. We want to understand. We want to explore. We want to know what's out there in the cosmos and how it all works. That drive, that fundamental curiosity, has led us from caves to skyscrapers, from stone tools to space telescopes, from wondering about lights in the night sky to understanding the life cycles of stars and the evolution of galaxies. And that journey is far from over. We're still in the early stages of cosmic exploration. We've barely begun to understand the universe we inhabit. Every answer raises new questions. Every discovery reveals new mysteries. The more we learn, the more we realize how much remains unknown. So yes, there are strange things in space, things that don't make sense yet, things that challenge our understanding, things that might be natural phenomena we haven't encountered before, or might be something even more extraordinary. The wow signal remains unexplained. Tabby's star keeps dimming mysteriously. Odd radio circles hang in space, enormous and enigmatic. Giant cosmic structures challenge the cosmological principle. Voids stretch across hundreds of millions of light years, nearly empty. The CMB cold spot sits in the primordial radiation, colder than it should be. Przybylski's star contains elements it shouldn't have. Oumuamua accelerated for unknown reasons. Fast blue optical transients explode in ways we don't fully understand. Ancient stars push the limits of cosmic chronology. Each of these is a puzzle piece that doesn't quite fit the picture we've assembled. And that's okay. That's actually exciting. Because those ill-fitting pieces are telling us something important. They're telling us that the picture is bigger and more complex than we thought. They're telling us to look closer, think harder, and remain open to possibilities we haven't considered. The universe doesn't owe us easy answers. It doesn't have to make sense on our terms or conform to our expectations. It simply is what it is, following the laws of physics wherever they lead, producing an endless variety of phenomena across vast expanses of space and time. Our job as curious humans is to observe, to measure, to hypothesize, to test, and gradually to understand. Sometimes that process is frustrating. Sometimes the answers come slowly. Sometimes we think we understand something only to discover we were wrong or incomplete. But that's the nature of the endeavor. Science is hard because the universe is complex. Understanding requires effort, patience, and humility. But oh, is it worth it? Every time we solve a mystery, every time we understand something that was previously puzzling, we gain something profound. We expand the boundary of human knowledge. We see the universe a bit more clearly. We connect with something larger than ourselves, with the vast cosmos that is our home. We participate in a grand human project that spans generations, each contributing our small part to the ever-growing edifice of understanding. And even the unsolved mysteries have value. They inspire us. They drive us to build better instruments and develop better theories. They remind us that there's always more to learn, always new frontiers to explore. They keep us humble, preventing the arrogance of thinking we've figured everything out. They keep us curious, maintaining the sense of wonder that drove ancient humans to look up at the stars and ask, what are those lights, and what do they mean? We've come a long way since those ancient stargazers. We now know those lights are distant suns, some with their own planets, some dying in spectacular explosions, some barely born. We know the universe is vast beyond imagination, ancient beyond comprehension, and governed by mathematical laws we've partially deciphered. We know we live in an expanding cosmos that began in a hot, dense state 13.8 billion years ago and will continue expanding perhaps forever, stars burning out one by one until the universe grows cold and dark in the incomprehensibly distant future. We know all of that, and yet we still don't know what the wow signal was. We still don't know why Tabby's star dims so dramatically. We still don't know what odd radio circles are. We still have so much to learn, and that's beautiful. That means the adventure continues. That means future generations will have their own discoveries to make, their own mysteries to solve, their own moments of revelation when something that seemed incomprehensible suddenly makes perfect sense. That means the story of humanity's understanding of the cosmos is still being written, chapter after chapter, discovery after discovery, mystery after mystery. So the next time you look up at the night sky, remember this: those stars you see, those faint points of light, are part of a universe far stranger and more wonderful than our ancestors could have imagined. Some of those stars might be behaving in ways we don't understand, like Tabby's star. Some might contain bizarre chemical compositions, like Przybylski's star. Some might be ancient beyond measure, like Methuselah, witnesses to nearly the entire history of the cosmos. And in the darkness between the stars, invisible to your eyes but detectable with the right instruments, there are structures and phenomena we're only beginning to discover. Radio circles spanning distances your mind cannot truly grasp. Cosmic voids so empty that civilizations arising within them would think they lived in a nearly deserted universe. Signals that might have traveled across interstellar space carrying we know not what messages or meanings. Every photon of light that enters your eye when you look at a star has traveled across space, perhaps for years or centuries or millennia, carrying information about its source. Those photons are messengers from distant places and times, connecting you directly to the cosmos. And scattered among those countless photons are clues, hints about phenomena we don't yet understand, mysteries waiting to be solved by someone curious enough to look closely. Maybe one day, someone watching a video like this will be inspired to become an astronomer. Maybe they'll be the one who finally explains what odd radio circles are. Maybe they'll discover more interstellar visitors and determine whether Oumuamua was typical or unique. Maybe they'll develop the theoretical framework that explains fast blue optical transients. Maybe they'll build the instrument that detects another signal like the wow signal, and this time captures enough data to understand its origin definitively. Or maybe you won't become a professional scientist, but you'll remain curious about the universe. You'll follow the news when new discoveries are announced. You'll watch in wonder when new images from powerful telescopes reveal galaxies billions of light years away. You'll appreciate that you live in an age when humanity is actively exploring the cosmos, sending robots to other planets, detecting gravitational waves from colliding black holes, and imaging the supermassive black hole at the center of our galaxy. You'll understand that science isn't about having all the answers. It's about asking good questions and systematically working toward answers, even when those answers take decades or centuries to emerge. It's about being honest when you don't know something, rather than pretending to certainty you don't possess. It's about following the evidence wherever it leads, even when it surprises you or contradicts your expectations. And you'll appreciate that the mysteries we've discussed today as fascinating as they are, represent only a tiny fraction of what we don't yet understand. We don't know what dark matter is, despite decades of searching for it. We don't know what dark energy is, despite measuring its effects on cosmic expansion. We don't know whether life exists elsewhere in the universe, though statistically, it seems almost certain given the vast numbers involved. We don't know what happened before the Big Bang, or if that question even makes sense. We don't know whether our universe is the only one, or part of a vast multiverse. We don't know the ultimate fate of the cosmos, whether it will expand forever, collapse back on itself, or undergo some transformation we haven't imagined. These are big questions, profound questions, questions that touch on existence itself, on meaning and purpose and humanity's place in the vast scheme of things. And science is gradually, painstakingly, working toward answers, not through revelation or authority, but through observation, measurement, hypothesis, and testing. Through the patient accumulation of evidence and the careful refinement of theories. The process is messy and imperfect because it's carried out by humans, and humans are messy and imperfect. We make mistakes. We have biases. We sometimes cling to ideas longer than we should. We occasionally get sidetracked by interesting ideas that turn out to be wrong. But the scientific method, the underlying approach of demanding evidence and testing ideas against reality, gradually corrects these errors. Over time, wrong ideas are discarded and right ideas survive. Knowledge accumulates, understanding deepens. And every generation contributes to this growing body of knowledge. The astronomers who discovered the WOW signal contributed by detecting it and preserving the data. The astronomers studying Tabby's star are contributing by monitoring it continuously and gathering the observations that will eventually explain it. The teams discovering odd radio circles and fast blue optical transients are contributing by cataloging these new phenomena and beginning the process of understanding them. The cosmologists studying giant structures and the CMB cold spot are contributing by testing whether our models need revision. The researchers analyzing Oumuamua's data are contributing by giving us our first detailed look at an interstellar visitor. Each contribution is a small piece of a much larger puzzle. No single person can solve these mysteries alone. Science is inherently collaborative, building on previous work, sharing data and ideas, critiquing and refining each other's hypotheses. It's a global enterprise involving thousands of scientists across dozens of countries, all working together toward common goals of understanding. And the fruits of that collaborative effort belong to all humanity. When we learn something new about the universe, when we solve a cosmic mystery or make a startling discovery, that knowledge becomes part of our collective human heritage. It enriches all of us. It expands our perspective. It helps us understand our place in the cosmos. Think about what our ancestors knew about the universe just a few centuries ago. They saw the sun, moon, planets, and stars. They noticed patterns in celestial motions and developed calendars. Some cultures built sophisticated astronomical observatories and made precise measurements. But they didn't know what stars were. They didn't know how far away they were. They didn't know that the Milky Way was a galaxy, or that there were other galaxies. They didn't know about the expanding universe, the Big Bang, black holes, neutron stars, exoplanets, or any of the countless phenomena we now know exist. In just a few centuries, we've gone from fundamental ignorance about the nature of the cosmos to detailed understanding of its history, structure, and composition. We've measured the age of the universe to within 1% accuracy. We've detected planets orbiting other stars and begun characterizing their atmospheres. We've witnessed stellar explosions billions of light years away. We've detected ripples in space-time itself from cataclysmic events in the distant universe. We've sent spacecraft beyond our solar system, carrying messages for any potential alien civilizations that might one day find them. This is an extraordinary achievement. It's something our species should be genuinely proud of. Despite all our flaws and failings, despite wars and conflicts and injustices, humanity has also produced this magnificent body of scientific knowledge. We've turned our curiosity and intelligence toward understanding the universe, and we've succeeded remarkably well. But we're not done. Not even close. The mysteries remain. The questions multiply. Each answer leads to new puzzles. And that's exactly as it should be. A universe we completely understood would be a boring universe. A cosmos with no more mysteries to explore would rob us of the joy of discovery, the thrill of encountering something genuinely new and unexpected. So let's celebrate the mysteries. Let's appreciate the wow signal for being genuinely weird and unexplained. Let's marvel at Tabby's star's bizarre behavior. Let's be astonished by odd radio circles and giant cosmic structures. Let's contemplate the eerie emptiness of the Bootes void. Let's puzzle over the CMB cold spot and Przybylski's star's impossible chemistry. Let's wonder about Oumuamua's strange acceleration. Let's be amazed by fast blue optical transients. Let's appreciate that stars like Methuselah have existed for nearly the entire history of the universe, silent witnesses to cosmic evolution. These mysteries are gifts. They're invitations to wonder, to question, to explore. They remind us that the universe is vast and strange and wonderful. They remind us that despite all we've learned, we're still at the beginning of the journey. They remind us to stay curious, to keep asking questions, to never assume we know everything there is to know. And who knows what the future holds? Maybe within your lifetime, all of these mysteries will be solved. Maybe we'll detect another signal like the wow signal, this time with enough information to determine its origin. Maybe we'll figure out exactly what's causing Tabby's star to dim so dramatically. Maybe we'll discover that odd radio circles are caused by some previously unknown astrophysical process. Maybe we'll develop new cosmological models that naturally predict the existence of giant structures like the giant arc and big ring. Maybe we'll find entire populations of interstellar visitors and determine that Oumuamua was just the first of many we'll study in detail. Or maybe not. Maybe some of these mysteries will persist for generations, challenging scientists long after everyone watching this video has passed away. Maybe they'll become classic unsolved problems in astronomy, studied by future researchers using instruments and techniques we can barely imagine today. Maybe one day, centuries from now, historians of science will look back at our era and marvel at how we struggled with questions they find elementary. Either way, the journey continues. The universe remains the universe, vast and ancient and complex. We remain curious apes on a small planet, looking outward and asking questions. The tools get better. The data gets more precise. The theories get more sophisticated. And gradually, incrementally, our understanding grows. That's the story of science. That's the story of human curiosity and ingenuity applied to the greatest questions we can ask. Where did we come from? What is the universe made of? How does it work? Are we alone? What does it all mean? We don't have complete answers to these questions, but we're working on it. We're gathering data, building models, testing hypotheses, and gradually piecing together the cosmic puzzle. The mysteries we've discussed tonight are part of that ongoing process. They're the rough edges, where our current understanding meets the unknown. They're the frontier, where today's puzzlement might become tomorrow's breakthrough. So thank you for joining me on this exploration of cosmic mysteries. Thank you for being curious enough to wonder about strange signals from space, about stars that behave in unexpected ways, about enormous structures that challenge our understanding, about visitors from other star systems, about explosions we can't explain, and about stars that have witnessed nearly the entire history of the universe. Keep that curiosity alive. Keep wondering. Keep questioning. Keep looking up at the night sky with a sense of awe and appreciation for the magnificent, mysterious cosmos we inhabit. Because up there, right now, strange things are happening. Signals are propagating through space. Stars are behaving in ways we don't understand. Structures are evolving on scales we can barely comprehend. And we're here, on this pale blue dot, trying our best to make sense of it all. It's a beautiful endeavor, It's a worthy pursuit. And the story is far from over. The universe still has secrets to reveal. Mysteries still wait to be solved. Discoveries still wait to be made. And perhaps, just perhaps, one of those future discoveries will be made by someone who first became interested in astronomy by learning about unexplained phenomena, by hearing about mysteries like the ones we've discussed tonight, and by realizing that the universe is far stranger and more wonderful than they ever imagined. The WOW signal, Tabby's star, odd radio circles, giant cosmic structures, the Boeta's void, the CMB cold spot, Przybylski's star, Oumuamua, fast blue optical transients. The Methuselah star. Remember these names, remember these mysteries. They represent the frontier of human knowledge, the boundary between what we know and what we have yet to discover. And remember that this frontier is always moving. What seems mysterious today may be understood tomorrow. What we can't explain now might be textbook material in a generation. But new mysteries will emerge to take their place, because the universe is endlessly inventive, endlessly complex, endlessly fascinating. That's what makes science exciting. That's what makes astronomy rewarding. That's what makes being a curious human in this cosmic age such a privilege. We live in a time when we can detect gravitational waves from colliding black holes, when we can image planets around other stars, when we can study the early universe in unprecedented detail, and when we can seriously contemplate questions about the nature of reality that our ancestors couldn't even formulate. We also live in a time when we can honestly say, we don't know about many things, and that's okay. Not knowing is the beginning of discovery. Uncertainty is the precursor to understanding. Mystery is the invitation to explore. So embrace the mysteries, celebrate the unknowns, and stay tuned, because the universe isn't done surprising us yet. Not by a long shot. The strange things in space are still out there, doing their strange things, waiting for us to understand them. And one day, perhaps sooner than we think, perhaps later than we hope, we will. We'll look back at these mysteries and smile, understanding at last what seemed so puzzling for so long. Until then, keep looking up, keep wondering, keep questioning. The cosmos is vast, ancient, and strange. And we're lucky enough to be here, able to observe it, study it, and gradually unravel its secrets. Thank you for watching. If you enjoyed this deep dive into cosmic mysteries, please consider liking this video and subscribing to the channel for more explorations of the strange and wonderful universe we call home. The journey of discovery continues, and I hope you'll be part of it. Clear skies, and keep wondering about the universe.